Welcome to lecture 59 of the rings and modules course. In this lecture, I will discuss about structure theorem of Artinian rings. Let me start. So, in the last lecture, we have seen that the structure of Jacobson radical in an Artinian ring, it is equal to the nil radical, and it is also Jacobson radical is nilpotent in a commutative Artinian ring. So, now let me start with the following theorem. Furthermore, properties of Artinian rings. Every commutative Artinian ring is semi-local. Every Artinian ring is commutative Artinian ring is commutative ring with unity, of course. With unity is semi-local. So, what is that meaning? So, that is there are only finitely many maximal ideals in a commutative Artinian ring. Okay. So, now let us prove this. So, let me start with let R be a commutative Artinian ring of course with unity. Okay. And we proved in the previous lecture, we proved that the Jacobson radical of R means intersection of all the maxima ideas of R. So, then this is intersection of finitely many maxima ideals. Okay. So, let us say this is M1 intersection M2 and so on intersection with Mn, let us say, where Mi's are maximal ideals. In R. Okay, where Mi's are maximal ideals in R. So, now the claim is the following: the only maximal ideals of R are Mi's. Okay. The only maximal ideals are precisely these Mi's. Okay. So, for that one, let us proceed the following. We already proved that the Jacobson radical of an commutative Artinian ring is nilpotent, that is Jacobson radical of R power R. So, this is equal to 0. So, for some R natural number R. Okay. So, therefore, 0 is equal to Jacobson radical of R power R. So, then this is M1 intersection M2 and so on intersection Mn whole power R, but this contains product M1 and so on into Mn this whole power R. Okay. Why? Because the product of ideal is contained in the intersection of the ideals. So, because of that, therefore, this is product is contained in this, but this is equal to M1 power R and so on into mn power r, because we are in a commutative ring. Okay. So, thus we have m1 power r and so on intersection mn power r. So, this is nothing but the 0 ideal. Okay. So, thus we get this. Now, let m be any maximal ideal in R. Okay. Let us start with any maximal ideal m. So, this means that m contains 0 as we know. So, this contains the product m1 power r and so on into mn power r. Okay. So, then this m contains some mi power r for some I. Okay. So, this follows since mi's are mi's and m, these are prime ideals. Okay. So, by using these properties, so we can say that this m contains mi power r, or we can show by contradiction. Suppose if none of the mi power r is contained in m, then we can derive a contradiction. So, therefore, this m contains mi power r. So, this implies that m contains mi. Why? Because for if you take any element a belongs to mi, if you take any element a belongs to mi, then a power r, this belongs to mi power r, but this is contained in m. So, this implies that a power r belongs to m, but m is a maximal ideal, therefore, it is a prime ideal, therefore, a belongs to m as required. Okay. So, therefore, m contains mi. Now, since mi is a maximal ideal and we get that our m must be equal to mi. Okay. So, mi is a maximal ideal, mi is contained in another proper ideal m, therefore, m should be equal to mi. Okay. So, thus if we start with any maximal ideal in R that is equal to mi for some I, that means that m1, m2, mn, these are the only maximal ideals of R. Thus, R is semi-local. It is a semi-local ring. So, this finishes the proof. So, now let me recall one result from ring theory part. So, it is called Chinese remainder theorem. So, Chinese remainder theorem. Let us see what it says. It says the following. So, let R be a commutative ring with unity. Okay. So, let I and j both are be ideals in R such that I plus j is equal to R. So, that is there is a name for this. So, that is I comma j, these are co-maximal, or another name is co-prime. Some books use the word co-prime, some books use the word co-maximal. Okay. So, I will use the word co-maximal. If I and j are two co-maximal ideals in R, so then the first thing is I intersection j is nothing but ij, intersection equal to product, and the second one is the natural map, let us say phi, from R mod I j or I intersection j. So, then this two R mod I cross product R mod j, this cross product ring. So, defined as so phi of x plus I j. So, this is equal to x plus I comma x plus j, the tuple. Okay. So, for every x belongs to R. If we look at this natural map, so this map is an isomorphism of rings. Okay. This natural map will be an isomorphism for the rings. Okay. So, this theorem now I am going to use. So, that is the reason I am taking this, Okay. So, now let us prove this. Proof, I think the proof it was proved in the ring theory part portion. Okay. So, I am just leaving the statement. So, now let me go to one proposition. Okay. So, I will write here. So, it says the following: let R be a commutative ring with unity. So, let I comma j be co-maximal ideals in R. Okay. So, that is I plus j equal to R. So, then I power m comma j power n are also co-maximal R for any m and n natural numbers. Okay. So, let us look at the proof. So, given that I plus j is equal to R. Okay. Now, what we need to show? We need to show that I power m plus j power n, this is equal to R, enough to show one belongs to I power m plus j power n. Okay. Then automatically it is equal to R. So, let us write, we have I plus j equal to R, let us write 1 equal to a plus b. So, for some a belongs to I and b belongs to j. Okay. Now, let us look at 1, this is equal to 1 power m plus n minus 1, this is a plus b whole power m plus n minus 1. Okay. Now, we can use the binomial expansion. So, this is nothing but summation I from 1 to m plus n minus 1 m plus n minus 1, choose I into a power m e power I into b power m plus n minus 1 minus I. Okay. So, this is and now I am rewriting like this, summation I from 1 to m minus 1. So, m plus n minus 1, choose I into e power I into b power m plus n minus 1 minus I plus, okay. So, summation I from m to m plus n minus 1 m plus n minus 1, choose I into a power I b power m plus n minus 1 minus I. Okay. So, now what we can do is I is at most m minus 1, then I can common b power n. Okay. So, b power n into summation I from 1 to m minus 1 times m plus n minus 1 choose I into a power I b power m minus 1 minus I. Okay. So, this plus here I can common a power m, if I common a power m. So, let us look at what left out term. So, summation. So, this is rest of the term summation j from let us say 0 to n minus. So, what I am taking j is equal to I minus m. Okay. So, this is something like this. J is, if I equal to m, j is 0, and if I equal to m plus this is n minus 1, then this is m plus n minus 1 choose I, sorry, this I want to be j. So, that means that j plus m into a power j b power m plus n minus 1 minus j minus m. Okay. So, like this. So, then this is clearly, this is an element which belongs to R, this is an element which belongs to R, because the powers are always non-negative. Therefore, this belongs to the this belongs to j power n plus this is I power m. Why? Because a power m belongs to I power m and b power n belongs to j power n. Okay, because of this reason. So, thus 1 belongs to I power m plus j power n. So, this means that I power m plus j power n, this is equal to R as required. Okay. So, this finishes the proof. Okay. Therefore, that I power m comma j power n are comaximal. Okay. So, now let us come to the theorem, structure theorem, Artinian rings, commutative Artinian rings. Okay. So, let R be a commutative ring with unity and R is Artinian. R is Artinian. Then R is precisely, then there exist maximal ideals, let us say m1, m2 and so on mn, okay, maximal ideals m1, m2 in R, in maximal ideals of R, such that m is, sorry, our R is isomorphic to R mod m1 power R cross R mod m2 power R cross and so on cross R mod mn power R for some R. For some R belongs to the natural number. Okay. So, let us see the proof. So, we already shown that, we proved that Jacobson radical of R So, this is M1 intersection M2 intersection and so on intersection Mn, okay, for some maximum ideals Mi is contained in R, okay, for some maximum ideals of R. And not only that, Jacobson radical of R, power R is it is a nilpotent, therefore, power R equal to 0 for some R belongs to the natural number, okay. And not only that, okay, so this means that, so 0 is equal to M1 intersection and so on intersection Mn power R, but this contains M1 like what we have done in the previous proof, M1 into the product Mn whole power R. So, this is same as Mn power R and so on Mn power R. So, that means that all these product is 0, Mn power R and so on Mn power R. So, then this is 0, okay. So, now since if you look at M1 power R, M2 power R and so on Mn power R, these are pairwise co-maximal ideals. Why? Because any two distinct maximum ideals, any two distinct maximum ideals are co-maximal, okay. So, therefore, their powers also co-maximal by the previous proposition. So, therefore, these are all pairwise co-maximal ideals. So, therefore, by applying the Chinese remainder theorem, so we get that somewhat repeatedly we are applying R, this is equal to R mod 0, but this is equal to R mod M1 power R and so on product Mn power R. So, then this is isomorphic to R mod M1 power R cross R mod M2 power R cross product and so on cross product with R mod Mn power R, okay. So, thus this is our required expression for the structure for the commutative Artinian ring. So, now this finishes the proof. So, now just let me give a remark. So, what it says is the following: we know there exist Artinian modules, but not Noetherian, modules, okay. And similarly there exist, we have given many examples, okay. There exists, there exists Noetherian modules but not Artinian modules, and also, and of course there are modules which are neither Artinian nor Noetherian, neither Artinian nor Noetherian. And also we have seen there are Noetherian modules, Noetherian rings but not Artinian as rings, okay, but not as Artinian as rings. And of course, there are rings which are neither Artinian nor Noetherian, which are neither Artinian nor Noetherian. But whereas we do not have any example till now, we constructed that. So, Artinian ring but not a Noetherian ring. Now, we will prove that in the next lecture we will prove that every Artinian ring is every commutative ring with unity, and suppose it is Artinian ring, then it must be a Noetherian ring. Let me stop.